The positive protons and the neutral neutrons are what creates most of the mass and are in the center of the atom called the nucleus. The outside is mostly space, and that's where the negative electrons occur. If the atom were the size of a football field, then the nucleus would be about the size of a tennis ball. The values for the proton, electron and neutron are found in the data booklet. The most important thing to remember is the proton is positive, the neutron is neutral, and the electron has a negative charge. Unfortunately, the symbols for must be known, and they are not logical. Atomic number is not an A, mass number is not an M. Atomic number tells you what element it is because it tells you what the proton number is, and if the atom is not an ion, a positive ion, a cation, or a negative ion, an anion, then the proton number will also tell you the number of electrons. The mass number is the total number of protons and neutrons. You will be expected to manipulate those values, such as in this problem here, in order to work out number of neutrons, protons, and even electrons by looking at the charge. Isotopes, the definition must be memorized. You must know it's the atoms with the same number of protons but different numbers of electrons. You need to also know how to write it. So in this example here we've got chlorine-35. You can also write it in symbolic form. You don't need to put the 17 at the bottom. You can just write 35 with a superscript then Cl, because we know it's 17 from the periodic table. Here are some examples of carbon-12 and carbon-14 isotopes. Isotopes have the same chemical properties because they have the same number of protons, and that is what causes the number of electrons, and the electrons are what cause chemical properties. But the physical properties, of course, they have different masses, but also related to that is their density will be different, the rate of diffusion will be different, and also the melting and boiling points will be different because they have a different mass. Just quickly, there are some uses of radioisotopes. That's just to let you know their importance, but that won't be on the test. So I'll quickly flick over those. You can pause those and read those if you'd like. More importantly is the mass spectrometer is an instrument that we use to separate the radioisotopes. Heavier particles will get deflected less by a magnetic field, and lighter particles will get deflected more. So also their charge will also make a difference. If there is an ion with a greater charge, that will also get deflected more. So lighter and greater charge. You'll be expected to be able to do calculations to work out what the average atomic mass is that you find on the periodic table, now that you're aware that isotopes exist, and once you're given the percentage, you just times it out using this formula. I suggest you just find a logical way to understand that rather than memorizing the formula. So you need here to be able to do it for a single a graph, and you also need to do it here given data values. At worst, they can also make you miss one of these values, and you need to be able to do it with an algebraic calculation. Next, electron configurations. Normally when you put a light through a prism, it'll come up with a full spectrum here of visible light. So that will be used in a second. Firstly, you need to be able to work with the calculations. You also need to realize that these equations, what these equations are, they're in the data booklet. So they're just, this h here is Planck's constant, and this c here is the speed of light. So they are just values that you can get from the data booklet. This thing that looks like a V is actually a letter N, nu, and that is frequency, and it's not velocity. And this lambda thing here is wavelength. You might be familiar on the past physics, IGCSE. So really these equations are just converting between E energy and V frequency, and then there's the second equation that will help you work between frequency and wavelength. Going back to spectra now, when an electron is excited, it goes to an excited energy state, to a higher energy level, and then when it goes back down, it releases that energy in the form of a photon, and this can be different types of electromagnetic wavelengths. It doesn't have to be light. So for here we have the line emission spectra of hydrogen. This is also the continuous spectrum. Once you put it through hydrogen gas, you get a line spectrum that's emitted, or you can look at what's been absorbed, and that's the absorption spectrum, and that will just have the black spots with where that's been absorbed. Now this spectrum shows us many different things. The most important thing is it's releasing energy of set wavelengths. So as the electron transmits from a higher wavelength and back down, we can see that it's not random, but rather it is lines of specific wavelengths. And also these wavelengths get smaller and smaller, the distance gets smaller as you go into higher energy levels. That's called convergence. So if you look at the spectral line series here, you'll see that there is a clearer diagrammatic representation here. You also need to know that the names of these things, so the Lyman series, if any electron moves from the first and then comes back, it produces ultraviolet light. The Balmer series, if any electron moves from the second and then comes back, when it comes back it releases visible light. When any electron moves back to the third, it's the Paschen series, and that's infrared light. You can also see the diagrammatic representation here of it converging. As we go to back to the emission spectrum of hydrogen, we can see the convergence much clearer here on a much more accurate machine that breaks up the lines. As you can see, the longer it moves, the larger the distance the electron moves, also the more energy it has, so the shorter the wavelength. Here's a list of the actual values which you can work out using those equations, which will be in high level. Okay, and just a last diagram here showing you the convergence. This here is the spectral fingerprint of the elements. So we can see hydrogen much clearer in this one. We can see the convergence, the line spectra. So because hydrogen only has one electron, it's nice and simple and gives us the sort of the baseline of where the orbitals actually are. If we look at other things such as sodium, helium, neon, mercury, you can see they all have their own single fingerprint, and we can look at substances that contain many different elements and analyze the lines to work out what is contained in that substance. Going to electron shells then, for standard level, you just need to be aware that each period gives you the shell. So 2818 or 288 is fine for the moment. These shells though, you need to know the number of electrons. So they're called the principal energy levels. So the formula is 2n squared. The principal energy levels and the number of electrons and the number of sublevels need to be known. So the values are given here in this table of sublevels, and also there is a more accurate description here, the electron configuration showing you the order and showing the convergence. Alright, but the easier way to do things here, the electron configuration, is working it out from the periodic table So as you read across, you can see that there's an S block, a P block, a D block, and an F block. The only trick is the 4s goes to 3D, not 4D. So you can just read an element off using the periodic table here. But students tend to get least confused if they put the effort in here to learning the order using this table. So you just write 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and it usually stops about there. If you want to go on, that's fine. And then you just draw diagonal lines. So the order will be 1s2, because the s's are always 2, the p's are always 6, the d's are always 3. So it's 1s2, 2s2, 2p6. You can also expand that out further to 2py, 2px, and 2pz. Well, we won't be doing that. 1s2, 2s2, 2p6, 3s2, 3p6, then you jump to 4s2, 3d10, 4p6, 5s2, jumping to 5s2, and then you go back to 4d10, 5p6 in that manner. So the electron configuration is just written as seen here. The energy level first, then the sublevel, the number of electrons. Each sublevel can only ever fit 2 electrons. And we can also write this in little boxes here. So the boxes need to be in the correct height according to what their energy level is. Alright, writing these little boxes there, we need to be aware of the names, unfortunately, of these things as well. So you fill it in the lowest order first. That's called the Aufbau principle. There are 2 exceptions to this, and that's chromium and copper, and these are very important because they get tested on all the time. The chromium is more stable if all of the suborbitals, and same with copper, are either a half field. So rather than having 3d6 with one orbital fully filled, it's better having all of them half filled. So the 4s electron pops up into the 3d4, it pops up to become 3d5. Same with copper, instead of having a 3d9 with just one half full and a 4s2 full, the 4s2 jumps up, so it's 3d10, 4s1. So you need to know that as there are exceptions to the rule, especially the Aufbau principle. Also, when you're drawing for ions, be aware that if there's extra electrons or loss of electrons, that the electron configuration, you've minused an electron or added an electron for that. Another exception to that rule, so these are the second most important exception for learning these things, is for the transition metals to take the electrons from the 4s's first before you take them from the 4d's. So there are some examples here if you can stop and have a look through. When you're drawing these electron configurations, you can draw it much quicker by taking the electron configuration of the noble gas that just occurs before it, and then just continuing on the electron configuration from that noble gas. So commonly it's done with argon, because by the time you get to argon it's quite big. So you can get rid of the 1s2, 2s2, 2p6, 3s2, 3p6. Don't write that, and just put argon in square brackets and then continue on with what's left for the electrons. And you can also do that with the other noble gases. So, moving on, there are some tables here showing you the number of electrons that can fit in each sublevel and the main energy levels. This is important to know. Have a look at the S's, they're just round. The D's are quite strange. The p orbitals are more sort of dumbbell shaped and just follow the x, y and z axis, so be able to draw those just by drawing an x, y, z axis and just drawing the dumbbell shapes on the correct axis. Completing these orbital diagrams now. Aufbau principle was starting with the lowest energy and working your way up. You'll need to work out that from the diagram. Hund's rule is to make sure that you have put a single electron in all of the boxes for a sub-level, which only occurs for P's and D's because S's only have one. So fill in the one in each of the 3 for a P, or one in each of the 5 for a D suborbital, and make sure they're all going in the same direction before you put a second electron in a box which will go in the opposite direction. Putting them in the opposite direction, by the way, is the third principle. That's called the Pauli exclusion principle. Alright, so here we have some problems: lithium, fluorine, potassium, nitrogen, oxygen. Pause the video and see if you can work those ones out. And the answers are here: lithium, fluorine, potassium, nitrogen, and oxygen. Here's a summary of the rules, and now we're moving on to a high-level work. Alright, important here to realize that as you reach the convergence level, you're reaching the point where the electron is getting so far away that it will just eventually pop off. Alright, so the highest amount of energy that an atom gives off, as it converges, you'll see that reaches the ionization energy level. The ionization energy is the amount of energy required to take an electron off. You'll need to know the full definition of that, which will be in the next unit. So, going back to those equations then, you'll actually have to be able to work out, make sure you're aware of the units. Frequency is per second, hertz, you might know that. The other units for the constants are in the data booklet. Energy is in joules. So you'll be expected to be able to work that out. So have a quick look at this problem 1. Stop the video and try and work it out first, and then have a look at the answer, and same for problem 2. Also stop now and we'll go through your workbook and see if you can do the workbook problems as well. Alright, ionization energy, well, the definition's given here. It will be covered again next unit. Don't forget to say that it's 1 mole of electrons, and importantly you need to know that for your calculations, which you would have worked out when you're dealing with a photon that's not in moles. So you have to work out what the energy of a single photon is to work through frequency and wavelength. And the chemical equation for ionization energy, it's in the gaseous state, to make sure you say that and write that, the little g. Delta H is positive, which we'll learn later in unit 5, sorry, unit 6. So that realize that delta H positive, that just means that you have to put energy into the reaction. You haven't got energy out of it, so it's taken energy to remove this electron. Okay, what affects the ionization energy? If there are lots of protons, so especially if it's in the same period, that means that the electrons are all about the same level, so they're about the same distance from the nucleus. The size of the nuclear charge will matter, so the larger the nuclear charge, the larger the ionization energy. Also, the energy that the electron has, so if it's further away from the nucleus, it's easy to remove. Okay, so here we have some pictures here. You can see nuclear charge. So the larger the nuclear charge, the larger the attraction, the more difficult it is to remove it. Make sure you mention attraction there. It's obvious, but often needs to be said. And here we have electrons are further away from the nucleus because they're in a larger shell, so they'll have less attraction and be easy to pull away as well. The other thing to mention also is electrons on outer shells also have repulsion from electrons on the inner shells. This is called electron shielding, and that's actually a third factor that determines how difficult it is to remove an electron. So as you can see here going across the period, the ionization energy increases as you go across because the nuclear charge increases, but you're in the same shell. So there's a diagrammatic, there's a table here that shows there's quite a strange thing that goes on with this. It doesn't just constantly increase the ionization energy as you're going along a period, and that is because the energy as you go across, you can see aluminium here. Aluminium actually jumps to a different ionization, a different sub-level. There's also another conflicting part from phosphorus to sulfur there, where there's a slight decrease. Okay, so removing an electron from the p sublevel is a lot easier than removing it from the S3s sublevel, the 3p sublevel, and the explanation for that would be because it's a different sublevel. It's slightly further away, so that the distance is increased. So that what makes it easier. Now that is in conflict with the fact that the number of protons are always increasing. So there's this balance here of increasing nuclear charge and increasing distance. And for this particular case, because it's jumped to a p sublevel, that has been more significant than just increasing by one proton. Nowadays, you continue down, aluminium, silicon, phosphorus, sulfur, chlorine, argon, they're all in the same SP sublevel, so they're all the same distance, so you'd expect a constant increase in ionization energy because there's an increase in nuclear charge. The slight decrease from phosphorus to sulfur occurs because after 3p3 you're adding electrons that are in opposite spin and they repel, so there's a slight mutual repulsion there. So it's easier to remove that electron because it wants to go because it's slightly repelled, and so that's why there's a minor drop there, and then it goes back to increasing again for chlorine and argon, even though that minor repulsion is still there and you're doubling and tripling it. The effect of the nuclear charge outweighs that. So you can see an explanation, written explanation there. And most importantly is the diagrammatic picture here. You need to be able to explain that, just like I said before. So you can see it's all about what sub-level it's in and whether or not the protons or nuclear charge are increasing. So you can see the dips occur when you move from one S to another S, which is increasing distance, or an S to a P, but within the same sub-level, or whether there's electrons going into mutual repulsion. Going down a group then, you can see that the ionization energy decreases because you're increasing quite significantly the distance through a larger shell, a larger distance, and there's also nuclear shielding going on. The next thing, which is very similar, is the successive ionization energy. This is how you write the ionization energy, the second ionization energy. Make sure you've written an ion, so there's one electron gone already. Make sure you've written everything in the gaseous stage. This here is a little easier because the nuclear charge is now a constant, because all you're doing is just constantly stripping away electrons from the same element. So you can see in this last picture here, this one here is for calcium. So we know that the nuclear charge doesn't change. The only thing we're doing now is continually stripping away electrons. So there's no jumps up and down, it's just continually getting harder and harder. And here you can see quite clearly the S electrons, they're getting pulled away, and then it jumps, the next 8 ones are S and Ps. So there's the jump, the first jump there, so that's the jump from the main energy level, and then the next jump is the next 8 electrons, and then the final 2 are the 1s electrons. So that gives you a much clearer indication of main energy sublevels. So you can see the sub-energy levels are pretty much all very constant. So that's probably the best the second best evidence besides the mathematical equation as evidence. This is probably the second confirmatory evidence of or justification for giving these things the levels, main energy levels and sub-levels that we do. So you can just read along there for number of electrons to be removed, and you can confirm by the jumps where the sub-levels are and compare that to the electron configuration to work out what the atom is, the element is.